Hey there, I want to return to the curve fitting video and do something a little more complicated than we've done in the past video or two. Um, Figures I sit down to record the introduction and there is now a police helicopter circling in the general vicinity. I guess Los Angeles, what can you do? Hopefully it won't come through on the audio too much. So I want to go back to curve fitting and I'm going to look at a more complicated problem that is extremely nonlinear. It's going to have different parameters on different sides of like x equals 0 or x, x negative, x positive. So it's going to have different parameters on each side of our independent variable. Some of those parameters are going to be shared between sides, and it's going to be a nonlinear problem. So it's going to be relatively complicated problem. Now I have a bit of trepidation about this particular problem because it basically comes from some research I did back in my PhD days, and the physics involved is fairly complicated. So what I've done is basically just simplified it and taken out all the analysis steps that gets you to the point where you're ready to do this, in this case, a final curve fit. In the real case, there are multiple iterations through various loops and whatnot. So this is a simplified version of research I did maybe 15 years ago. So I'm not quite up to date on the physics of it, but I hopefully that's not going to be an issue. So like in previous videos, I'm just going to do a little section on the problem statement with slides and kind of show you what we're going to do, and then we're going to go into the actual coding. Now this, while it is a complicated problem, it can probably be handled by Python, which has a curve fit function, but we're going to use the actual minimize function from the optimization package. So that way you can take this as a more general method and apply it to whatever problem you need to. And while there might be better ways to do this, I'm just essentially going to brute force it so that this method is somewhat general and you can apply it to your specific type of problem. So yeah, let's get going. Now these data are from liquid helium going through the lambda transition, the superfluid transition. This is specific heat data over here on the y-axis in joules per mole Kelvin. And this variable on the x-axis, theta here, let's wait for this thing to vanish. Theta is essentially the distance from T lambda divided by T lambda. So it's a dimensionless distance from the transition point. So the positive values represent temperatures above the lambda point. Those are also coded in red, just to be specific here. So and the negative ones are for data below T lambda. So as we come here, we're cooling down, the specific heat begins to rise. It begins to rise extremely fast. We pass through the superfluid transition and we begin to cool down. And that's where we ended up, we stopped taking data. And now our problem is to model this and extract out some parameters that describe the physics of the system. So here's our model equation here. CP phi is equal to A over alpha, theta to the minus alpha, and this other stuff here. You can read it. But our problem is several fold. We don't know A, we don't know alpha, we don't know D, and we don't know B. Second problem is some of these parameters, like A has this plus or minus here. That means the amplitude, this amplitude term A, is different on either side of the transition. Likewise, D is different on either side of the transition. But you notice there's no plus or minus on the alpha or the B here. So these things are shared, these values are shared either side of the transition. So we have to do a least squared fit and pull out the values of the A's, the alphas, the D's, and the B's. So we're going to have 1, 2, 3, 4, 5, 6 parameters to fit to. And so we're just going to fit this rather naively. We're not going to do a lot of processing of the data. There are tricks and things you could do to make this an easier problem. But we're just going to do it in, as I said, kind of a naive manner and just brute force the problem. The only thing that I'm going to do that's a little out of the ordinary is change the algorithm that the minimization function in Python uses to actually calculate the minimum. A lot of these things require the derivative of gradient of the function with respect to these parameters that you're trying to pull out. And you notice that's going to give us an issue with alpha here, in that the derivative with respect to alpha can become infinite here, and that's kind of obvious just from looking at the shape of this this plot here. As the specific heat, as we get close to the lambda temperature, the specific heat shoots up very, very quickly. And I am occasionally going to show the data plotted in this form. This is the same data as before, just shown on a semi-log plot where the x-axis is on a log scale here. And then because we have negative numbers here, I just take the absolute value of the temperature on the cold side to flip it over. So this is the same graph as before. It just is a little bit easier to look at. It's the same idea. We're cooling down, cooling down, cooling down, cooling down. We go through the transition temperature, which on the log scale, 0 is at negative infinity. Then we keep cooling down, cooling down, cooling down like this. This is a little bit easier to look at just because the things are not changing as rapidly. And when I said that we wouldn't do any tricks to fit the data, that's true. But if just looking at this, hint, hint, this looks like a lot easier to fit than the actual function that I showed before where things, skyrocket near T lambda. Another thing I should probably say, if you're familiar at all with helium physics, the numbers that come out of this are looking a little strange. And I don't remember if I said this in the intro or not, but this is not pure helium-4. This is helium-4 with some helium-3 dissolved into it, deliberately dissolved into it. And if I remember correctly, it's about 15% helium-3. So it's a mixture of the two isotopes. So I've created a text file here called fit_lambda.py, and of course we're going to need to import our numpy library. So import numpy as np. We're going to need from scipy.optimize. We're going to need to import the minimize function. Oops, I'm typing exactly what I'm saying. Import minimize. And we're just going to import the plotting libraries too. So import matplotlib.pyplot. Pyplot, I'm missing a p, plot as plt. Okay, so let's just import our raw data. Now, I exported this from now at this point, decades old files that have tons of columns in there, so we're going to need to parse it down. But let's just call it for now cold data raw, and it's going to be mp dot load text, and I don't remember the name of the file. The name of the file is colddata.txt, so let's just go colddata.txt, and I need to close that up, and we're going to do the same thing for the warm data, and we're just going to change the word cold to warm, so we don't need that. Cold, warm, done. And now I want to change this actually. I want this to be raw first here. And then delete 4 characters, delete 4 characters. And I want to now just do this. So I'm just going to pull out the rows and columns that I need from that. I'm just going to call those theta warm and C warm for the specific heat. And I'm going to copy those lines. Come on, 2y, oops, that's why it's doing that. 2yy. Put, and now from here I'm just going to change warm to cold again. So we now have our data for the cold and warm side, theta and C respectively. And it didn't change it, did it? So let's do this again. Search warm, cold. There we go, that actually did it. So now let's just plot these data to make sure we've pulled them in correctly. So we're going to go down here and do plt.plot theta warm, C warm, theta warm, C warm, and just like that other plot, I'm going to make these circles and I'm going to make them red. And hopefully I typed that correctly because I'm just going to do this. Cold, cold, and I'm going to make these blue just like the plots in the slides, and plt.show. So let's hope this runs. So let's switch to our console, Python fit lambda, Yeah, it plots it fine. The temperatures stored in the data file are positive, so these, if we actually want it to look like the slides, we have to make this negative. So let's quit that, go back here, and we'll add in a minus sign here. And that looks right. So good. Let's go back to the code, and for the time being, we will just comment these out. Okay, so now we need to construct the error function, and I find it convenient to break that into two specific pieces. One function that's going to actually be the function we're fitting to, in this case, the model for the specific heat, and then another function that does the least squares part. So let's come up here and we'll define the specific heat function. And just for convenience, just to make it play nice with the way the rest of the code is going to be structured, I'm going to have it have a vector come in that's a parameter of vector p, and then our theta values. And I'm going to pull the parameters a, alpha, b, d, and whatnot from that parameter vector p. So for my test code, I'm just going to paste it in here. So a is the first component of the vector, alpha the second, and so on, b and d. So now all we need to do is just return the specific heat just from that formula. So I'm just going to again copy and paste it. This is the formula that was on the slide, the a over alpha term, the theta to the alpha minus alpha, and then the correction to scaling term. So this just calculates the specific heat for a given value of theta. So let's just actually make sure this runs. I'm going to switch to the console, and it should just do nothing, return nothing. Yeah, okay. Just to make sure there are no bugs there. So let's just clear out this to keep the everything nice and clean. And now we need to move on and construct the error function. And now the next thing is to create our error function, or objective function as it's often called. It is that's what I called it in my blog post code, so I'm going to call the same thing here. So I'm just going to again copy and paste from the test code here. This function takes a vector of parameters that you're trying to minimize, and then all the additional arguments which will be passed into this function. So yeah, so now we go on to actually define the function. And I'm going to define the parameters like this. So this vector q is going to contain a prime, alpha, b, and d. So now we need to calculate the specific heat. So we need to pull out, for example, on the warm side, we're going to need to pull out P0, which is the amplitude on the warm side, P2, which is going to be the alpha, I'm sorry, I'm saying P's instead of Q is Q0 is the amplitude on the warm side, Q2 is the value of alpha, and so on. So now we just calculate the specific heat for the values of our experimental theta warm, theta warm that's going to be passed into the function. So the specific heat as a function of these parameters, P is just going to be this. It's going to be C warm, and it's just going to call the specific heat function that we defined above and pass in the theta warm variables. Now we just do the same thing on the cold side. And we do that just basically by replacing, doing the same thing here, except our P value now contains the amplitude for the cold side and the correction to scaling term for the cold side, and then it's just specific heat cold, specific heat function, called with our new parameter vectors here, and then passing in our theta cold values. And now the last part is just to define the sum of the squares, sum of the squared errors, because we have the experimental data, we have our new calculated theoretical fit data, and now we just need to define the actual quantity that's going to be minimized, i.e. the sum of the squared errors. So let's just save it first, and we will just again, sorry I'm doing a lot of copying and pasting here, but yeah, I'm a bit out of it today and haven't had a sufficient amount of caffeine to actually do this in real time. So what I'm going to do, just to make it simpler, is calculate the squared error on the warm side. That's this value here, error squared warm, and that is just our C warm minus the C warm, the experimental values. And then we're going to square that. Same thing on the cold side. And then we're going to go down here, and what we're going to actually return is this. We are going to just sum the squared error of the warm side, sum the square error of the cold side, add them together, return that value. And that's that. So let's move on here and actually do the minimization. So let's see here. Let's just save this first. Here's where we're pulling in our data. We're plotting here. So we're going to need to provide a vector of initial guesses. And this is where I'm going to start saying that I'm going to fudge this a little bit and just pass in these vectors. Now this is not going to give us exactly the right answer. It's just going to get us close. This function, and this is why I had a bit of worry about doing this particular problem. This thing is actually pretty hard to fit and make consistent with the actual physics of what's going on. So these are not going to give us the exact results. Later on I'll just put in numbers that give us better results. But I just want to show the general process in this video, and if there's interest in future videos, I can go in and show how to refine these numbers and get better results. So these are going to be our initial guesses, and I'm just always making a note here that I'm passing in A prime, just how this vector is structured: alpha, B, D, D prime. So these are my guesses here. So save it. And now we just call the minimize function that we've imported from SciPy. So again, I'm just going to paste this in here. And this is the format of the minimize function. It takes our objective function, which we're actually trying to find the minimum of, the vector of initial guesses here, that's the Q, and then a bunch of arguments. So it's going to pass in all the arguments that are going to be needed here, our experimental data, the experimentally measured temperatures and experimentally measured specific heats. So that's going to be passed into the function in this arguments term here. And now I'm just going to go down and print out this results object. Did I spell that right? That's why I've been copying and pasting, because I am out of it today. Print results. Let's just see if this actually runs. It does not. So what's the issue here? Not supported. Let's find the error. Something is being passed in as a none, so something is probably not defined exactly right here. Let me just comment out this and see if the code runs. It should run. It's just pulling in stuff, files. So that runs fine. So something not being passed into the minimization function. These things are kind of opaque sometimes. Let's see here. I don't know. Oh, this function actually needs to return this thing. I'm used to MATLAB here, so return res. That should do it, I think. Yeah, there we go. We get good results this time. So this here, these are our return values, which are sort of close to the actual values. We get a value of 9 for the amplitude of the specific heat on the warm side, 8 on the cold side, an alpha of about minus 0.02, and then so on. So we can pull these values out of this object if we want. We get a success thing here. It comes back as true. This stuff up here is particular to the minimization algorithm we used. If you go back to the code, where is it? Minimize. Here it is. We set the method to Powell it's a derivative-free method, and since this function has issues with derivative evaluated alpha equals 0, this just kind of circumvents that issue from the get-go. So let's go from here and see how well this fit works. And I'll do that just by going back to this results object and pulling these values out directly. So let's go back to the code, go up here, and I'm just going to pull these right out of the results.x vector here. So now I just feed these vectors into our specific heat formula for the warm and cold side, and then plot those. So let's do that now. So we put this in, we just feed these back into the specific heat functions, pretty straightforward, and now we just plot these. So let's go down here and uncomment these. And we'll just put them here, plot it here. So we're plotting the theta warm, theta cold, and we're just making these a yellow line each. So let's see how this looks. Let's go here and run it. So yeah, pretty decent results here. On the cold side, I probably have to take the negative of that. Let me see how this is plotting here. So let's zoom in. Yeah, I have to put the negative theta values in here. So let's do that. So cold, 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 negative. Plot again, and this is what this looks like. So yeah, it's a pretty decent representation of our data. So let's go back here, and instead of doing plots, let's get rid of this minus sign. Let's just see if we could just do this as one change. Let's see how well this actually works. Change and do it as semi-log x. Save it. Oh, we have to do the minus sign again. Take it out here. There we go. So that's kind of a representation, a better, easier way to see see how well the data fits the actual thing. Let's phrase this again in English. Let's see how well our fit actually fits our experimental data. So we do it on a semi-log plot. You can see it a little bit clearer. It's not too bad. So yeah, it's pretty straightforward. Fit lambda. Yeah, it's just actually these numbers look a lot better than I thought they were going to. They're pretty close to the actual values now that I stare at them a bit. Couple little minor issues, but not too bad. So that's it, guys. Pretty straightforward. Back in the day, this gave me a little bit of a problem. It took me a day or two to figure out how to approach it because I was just thinking of it in terms of a curve fit problem rather than the underlying optimization problem. And that's why I've kind of harped on think of this as a minimization problem rather than a specific curve fitting problem. So I'm not sure what I'm going to do next. I know the next curve fitting video we're going to look at fitting a differential equation to some data and come up with a simple model of a lithium ion battery. And I'm going to do a couple of things which I probably should have done in this video, but it was already complicated enough. And that is look at how to address things when some parameters vary over orders of magnitude, which causes some problems with things like, what's the word I'm looking for, convergences and things like that. And since the mathematics is going to be, at least the physics is going to be a lot simpler than what we did today. At least a lot of people I know are not familiar with helium physics. We might look at the same lithium-ion battery problem and pretend we don't really have any idea of what the values of the resistances and the capacitances are. So we'll use a global optimization algorithm to kind of search the parameter space for something that looks close to a local global minimum, and then from there we'll use that to feed into a similar to what we did here, using a local minimization function. Anyways, that's it for today, guys. Sorry I'm a little out of it today, so I'm not going to bother going back and cleaning up the audio or re-recording some things. Oh well, it's going to be one of those done is better than perfect things, and until next time, take care.